Okay, have a good day, students. Today we are going to see about capacitance of two-wire transmission line under the unit electrostatics in dielectric medium. So already we have discussed a lot about this dielectric medium and about the parallel plate capacitor, um, then cylindrical capacitor, spherical capacitor, etc. Now here we are going to see about the capacitance of two-wire transmission line. So here we are considering two wires, one is A and another one is B, and it has they have the radius of R. Okay, it has the radius of R, and they are separated by a distance of D. They are separated by a distance of D. Now we consider a point P at the bid of the wire, so that is from A to P, the distance is x, so that the remaining distance is d minus x. And here up to this, if you cancel this r value, then you will get d minus r here. So these are the consideration. So it's a long wire, and we are considering only 1 meter of length of the line. So the charge of 1 meter line is equal to q, and the charge density is given by lambda is equal to q by L. So lambda is equal to q by L. So q is equal to lambda into L, where L is equal to 1 meter and q is equal to lambda. Now apply the Gauss law to find the electric field due to the wire A. So for that you consider the wire as a cylinder with an imaginary cylinder. It's a closed cylinder, and it is having a radius of x and the length is 1 meter. Now the flux coming out of the cylinder, is equal to the charge enclosed. So flux is mentioned as psi here. Psi is equal to q, and it is again equal to the product of this flux density and the 2 pi x into L. So that is the volume. So 2 pi x into L, that is equal to the total amount of charge. So D is equal to Q by 2 pi XL, and L is equal to 1, so again Q by 2 by X. Now the relation between E and D is given by E is equal to D by epsilon, and E is equal to Q by 2 pi X into epsilon. And if you want to find the electric field due to A, so the A is equal to Q by 2 pi epsilon x, and EB is equal to here this B is equal to Q by 2 pi epsilon into D minus x, this distance matter. Now E is equal to the sum of the electric field due to A and B, so EA plus EB. Now E is equal to Q by 2 pi epsilon x and Q by 2 pi epsilon into D minus x, as we have written here. So just add, take the common term outside, and that is multiplied the inside terms as 1 by x plus 1 by d minus x. Now the electric field is a negative potential gradient, as we have already studied. So E is equal to minus dV by dx, change in potential with respect to x. Gradient is meant for the gradually decreasing or increasing component. So here it is the potential minus dV by dx. So dV is equal to minus E into dx. Now here you can see the V value, that is by integrating this equation. V is equal to integral of minus E into dx. So the potential is nothing but always the moving of a positive charge from B to A here. So D minus R to R while moving a charge from B to A. So V is equal to, the limit is mentioned here, D minus R to R. Instead of E, you are substituting the value Q by 2 by epsilon into 1 by x into 1 by d minus x into dx. And the x derivatives are taken inside the integral value. So integral over d minus r to r, and the values 1 by x in plus 1 by d minus x. And in the next slide we can see the q by 2 by epsilon naught. The negative slide is replaced by interchanging the limit r to d minus r, and you are applying the integration. So 1 by x plus 1 by d minus x, limits are d minus r to r. I think, sorry, it's not here. In the next step, we apply this. So log x r to d minus r, and then log d minus x by minus 1 r to d minus r. So for this you will get the value after substitution. You will get the value like this. That is 2 d minus r by r. Okay, so this 2 and this 2 will get cancelled. So there is no 2 here. So that you can write q is equal to this 2 is not here, pi into epsilon v divided by ln of d minus r divided by r. Now we can use this relation. Q is equal to C into V, the value of capacitance multiplied by the potential. So C is equal to Q by V. So from this, what we want to find is capacitance. So C is equal to Q is this value. So Q by V. So there the V value will be get cancelled, and you will get pi epsilon divided by ln of d minus r divided by r, then that is farad per meter. So that is a exact equation. Now if you let C prime be the capacitance per conductor, capacitance per conductor, there are two conductors are there. So when they are in the series combination, so it is mentioned as C prime and C prime. It won't change, C prime and C prime. So it will be like this: the combination of C prime, and another one is, it is nothing but the mentioning the two wires. So since it is serial, totally it is C prime and C prime. And here this is given by C is equal to C prime into C prime divided by C prime plus C prime, which is nothing but C prime square by 2C, and you will get this one C prime and C prime will get cancelled. So you will get C prime divided by 2, and this C prime is equal to 2C. Now C prime is equal to, already we know the value for C, that is equal to pi epsilon. So 2 into pi epsilon divided by ln d minus r divided by r. So farad per meter per conductor. This is the capacitance for a particular conductor. So C prime is equal to this value. Okay, fine. And now let us move on to the next topic, that is energy stored in a capacitor. Energy stored in a capacitor. So here you can see capacitor is charged using a DC source. capacitance. Capacitor is charged using a DC source. It's a parallel plate capacitor. The power supply is given. And this is plus and minus. This is potential. Here it is plus and minus. So this is the capacitor. And the voltage across the capacitor, that is given by V. So it's a closed loop. Now here the work done, d omega be the work done. So to establish a charge of dq. So normally we say that W is the work done to move the positive charge from one side to another. So here it is the d omega is the work done, and V is equal to d omega by dq, and whereas d omega is equal to V into dq. Now substitute V is equal to Q by C. Okay, V is equal to Q by C. It's all the relation already we know. So Q by C into dq. D omega is equal to Q by C into dq. Here the voltage across the capacitor is small v. What we applied is not exactly passed here. So the voltage across is small v. So here you should put it as small v, small v, yes. Now let us see. Let us solve this. When the capacitor is fully charged to capital V, okay, when the capacitor is fully charged, if this complete potential applied is utilized here, then it is fully charged. When the capacitor is fully charged to V, then the charge should be, the total charge should be capital Q. So the work done to establish a charge of Q, that can be obtained by the integration, okay, by integrating. Work done to establish a charge of Q. So normally it's mentioned as dq. By applying small v, will small change in charge. If you have a v, then this q. So how it is obtained? So d omega, integral of 0 to w, that is the total work done, and integral over, that is equal to 0 to capital Q. So Q by C into dq. Q by C into dq. Now you can write W is equal to 1 by C, and that is Q square by 2 q square by 2, 0 to q. That is equal to 1 by c, or you can write it as q square by 2c. So this can be again written as q into q by 2c. For one q, you have to substitute the CV value. So 1 by 2 into CV into q by c. So c and c will get cancelled. So the total work done is equal to 1 by 2 V into Q. 1 by 2 V into Q. Okay. Now if you consider a system of having n number of point charges, if you have a n number of point charge, the energy stored in the system. So therefore the energy stored in the system, that is given by 1 by 2 into V1 Q1 plus V1 Q1 plus V2 Q2 plus dot 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 Vn Qn. So in general you can write, in general you have to write this as W is equal to 1 by 2 summation of I is equal to 1 to n, and we can write as Vi Qi or Qi Vi, whatever it be. And from the previous equation, that is W is equal to Q square by 2C. Q square by 2C, this one. Since W is equal to Q square by 2C, and here you apply Q is equal to CV, and this is C square V square by 2C. Here this is get cancelled. Therefore W is equal, that is work done, is equal to half CV square joules. This is the work done. That is the energy. Okay, so energy density is equal to, in the next line you write, energy density is equal to energy divided by volume. Here you have half CV square, that is the energy, and area into the distance between the two plates, A into D. So therefore it will becomes 1 by 2 1 by 2 divided by A into D. This C can be written as epsilon A by D. This is, we have seen this in the previous derivation, into V square. And here this A and A will get cancelled. Therefore it will becomes 1 by 2 epsilon into V square divided by D square. V square by D square. So this V square by D square is written as 1 by 2 epsilon into E square. Okay. So here this can be written as again 1 by 2 epsilon into E into E. So in order to relate this with the energy density, so we can write energy density that is equal to 1 by 2 into D into epsilon. So the energy density is equal to of D into, sorry, it's E. Here this is D. Okay. So this value takes D value, so D into E. That's what I have written here. Therefore, the energy is equal to just energy is equal to 1 by 2 D into E into volume. This is energy density. And W is equal to 1 by 2 integral of V D dot E vector into dV. This is the expression. Okay, so this is how the energy is stored inside. Now the last topic, the force of attraction between plates. It's a small topic. So you know that between the oppositely charged plates, there's always there will be a force of attraction. Uh, then the F is an external force that is applied to move the plate B from point 1 to point 2. So first you draw the two plates here. Let me draw two plates. One is A and another one is B. This is A, this is B, and this is P1 and this is P2. Position 1 and position 2 of B, and this here it has positively charged plate, and this is negatively charged plate. They are separated by a distance of D, and this distance is dx, change in so force applied. Now a force is applied externally to move the P, that is plate B, from the position P1 to P2. So the work done is stored in the form of energy in the additional volume A into dx. Okay. So in addition there is a value. This has a area. This is a plate actually. This is a plate like this. Okay. So this has a area. So area into dx. Now work done is equal to additional energy. So work done, how much work is done? The force is applied on B to move from P1 to P2. So that is given by F into dx, force into displacement. That is equal to additional energy, that is the energy density into volume. Therefore, we can write f into dx is equal to, from the previous case, of epsilon e square into a into dx. This is the energy density, epsilon into e square. Here you can see this in this equation, epsilon into e square, that is energy density, into volume is a into dx. So this is a force, okay, so then it will be mentioned in terms of Newton. So dx will be removed, and you can write f is equal to of epsilon e square a Newton, while writing that small letter Newton, and F by A is equal to force per unit area, that is given by of epsilon E square. So that's all. Okay, in the next class we will discuss the problems of this unit. So if you have doubt, you can hear the video repeatedly. So don't forget to subscribe my channel. Thank you students.